So here we go, me sticking to my promise of making a follow-up video on a Ken Sheriff blog. So I'm trying to take this really high-level guy's analysis and maybe boil it down, kind of do a little bit of the hard work for my students by reading this to them and using all my little teacher tricks to get this into their heads. Okay, so it says, the 8008's ALU circuit above looks like a mysterious collection of gates, but eventually I figured out the structure behind it. The starting point is a full adder that handles the sum operation. Now a full adder adds 3 input bits. You got your A and B, and then a C for a carry bit. Then it, not surprisingly, outputs the sum. The full adder is then heavily modified to support the logic operations yielding the ALU from the previous section. The logic operations are implemented by using the mode lines to block parts of the circuit, yielding XOR and or, rather than the more complex sum. So that's kind of comforting to know that summing things are the most complicated we'll get. But for now, it says here that the diagram below strips down the 8008's ALU circuit to reveal the full adder hidden inside. The gate in red generates the carry out from the 3 inverted inputs using relatively straightforward logic, and since the 8008 uses carry look ahead, this carry out signal isn't passed to the next ALU slice, but just used to generate the ALU output. So if you examine the possible sum cases, you'll see that the sum bit is almost always just the carry out inverted, except for the 0 plus 0 plus 0 and 1 plus 1 plus 1 cases. Thus, the sum bit can be generated by inverting the carryout and handling the 2 exceptional cases. The 2 gates indicated below handle the exceptions by forcing the sum output to the correct value. So it looks like when adding numbers, I can use this nifty little architecture here. And I'm saying architecture because it was decided that the AND gate is here and the OR gates are here and the NAND gate is there. Strange to think about math being in architecture. Let me get some more of Mr. Sheriff's words here, though, to use on you. Comparing the full adder with the full ALU circuit earlier shows that the mode lines support the logic operations. Once you have a full adder, generating the XOR is simply a matter of setting the carry in to 0, which is done by the M3 control line for the OR and AND operations. These are called mode lines M3 and M2 respectively. Comparing the full adder with the full ALU circuit earlier shows how the mode lines support the logic operations. Once you have a full adder, generating XOR is simply a matter of setting the carry in to 0, which is done by the M3 control line. For the OR and AND operations, the mode lines of M3 and M2 respectively disable all of the circuit except the gates labeled in green. So go up here, what's in green? Okay. So these are disabled when we're doing an OR or an AND operation. And that must come in the form of an instruction. So if you start with a full adder and extend it to support these operations, the 8008's ALU circuit is a logical result. So good job, ALU. Now we know what an ALU is doing. It is summing, it is XORing, it is ANDing, and it is ORing. That is not nearly as complicated as I originally thought. Now, Intel's earlier 4004 microprocessor had a simple ALU that only supported addition and subtraction, not many logical operations. So interestingly, the 4004's ALU circuit is almost identical to the full adder circuit shown above. So it's very likely that Intel designed this 8008 ALU by just extending the 4004, and this would explain why the 8008's ALU is generating carries internally, even though the carry look-ahead circuit made this a redundant thing. That paragraph really confuses me, but if I could summarize it, I think he's just saying it's not a big difference from this version to the 8008's. And he also says right down here now that this logic is very similar to the Z80's. Although the Z80's ALU is surprisingly only 4 bits. Oh my gosh, he has another article all on this that I'll have to read, and I just love the pictures. But that's for another time. Let me wrap this one up. The 8085 uses a different complex gate arrangement, and then the 6502, Mr. or Professor H now. Professor H's favorite is the 6502, which he is saying uses an entirely different approach. There are straightforward circuits for addition and or an XORing, and something we haven't talked about yet, which is a shift right. Apparently the 6502 is using pass transistor multiplexers to select the operation. So I'm going to leave you hanging on this article again, and I'll go ahead and make another video about the instruction decoding. But this was a nice little snippet of the 8008's ALU logic.